Chapter 3, Chemical Equilibrium, Class Life Sciences, Part 5, Equilibrium Constant. At the end of this session, students should be able to determine the equilibrium constant of a reversible reaction relative to concentrations Kc. According to the law of action of mass, when a reversible reaction has attained equilibrium at a given temperature, the product of the molar concentrations of the products divided by the product of the molar concentration of the reactants, each concentration is raised to the power equal to the stoichiometric coefficient appearing in the balanced equation, is constant. This constant is called equilibrium constant relative to concentrations Kc. That means what? For the general equation of a reversible reaction, A plus B gives C plus D, and small a, b, c, d are the stoichiometric coefficients, and the molar concentrations at equilibrium are concentration A, concentration B, concentration C, and concentration D. The expression of the constant of equilibrium relative to concentration Kc is concentration of products C and D over concentration of reactants A and B, each raised by the power which is the stoichiometric coefficient of the balanced equation. That means the concentration of product C to the power C and concentration of product D to the power D over concentration of product A to the power A and concentration of the reactant B to the power B. This is the general expression of Kc. Now, the constant of the reverse reaction, if the products are now the reactant, this is the reverse reaction, the constant K prime C equal, now A and B are the product, concentration of product over concentration of reactants, each one is raised to the power, which is the stoichiometric coefficient of the balanced equation. This expression is 1 over Kc, then K prime C equal 1 over Kc. Example, the equation of synthesis of ammonia, N2 plus 3H2 give 2 NH3. Kc equal concentration of NH power 2 over concentration N2 power 1 times concentration H2 power 3. This is the expression of Kc of this reaction. Remark, Kc is a constant without unit. Application 1. Consider the esterification reaction CH3COOH plus C2H5OH give the ester CH3COO C2H5 plus H2O. Acid carboxylic acid plus alcohol give ester plus water. The state of equilibrium is reached when the amount of each species is number of mole of CH3COH equal number of mole of acid equal number of mole of alcohol 0.33 mole, and number of mole of ester equal number of mole of water equal 0.67 mole. 1. Determine the equilibrium constant relative to concentrations Kc for this reaction, and 2. Deduce K prime C for the hydrolysis reaction, the reverse reaction. Solution of application. We have, I will write the equation by word equation, acid plus alcohol give ester plus water. At equilibrium, 0.33 mole, the number of mole of acid, and 0.33 mole of alcohol, 0.67 mole of ester, and 0.67 mole of water. Kc part 1 equal concentration of ester times concentration of water over concentration of acid times concentration of alcohol. H is raised to the power 1, which is the stoichiometric coefficient of the H component of the reaction is 1, 1, 1, 1. But in the expression, the reaction is concentration, but the given are number of mole, then the concentration equal number of mole over V, number of mole of ester over V, times number of mole of water, concentration of water equal number of mole of water over V, over concentration of acid equal number of mole of acid over V, times concentration of alcohol equal number of mole of alcohol over V. We simplify by V, same reaction mixture, same volume. It remains number of mole of ester times number of mole of water over number of mole of acid times number of mole of alcohol. Now we replace each term by its value. Ester 0.67 times water 0.67 over acid 0.33, alcohol 0.33 equal 4.12. This is Kc. Now the constant of the reverse reaction K prime C equal 1 over Kc equal 1 over 4.12 equal 0.24. This is the solution of application 1. Now application 2, consider the table given below that shows two sets of data for the reaction at 500 degrees. N2 plus CH2 gives 2NH3. We have two experiments at the same temperature, 500 degrees. The initial concentrations are different, 1 mole, and 0 mole for experiment 1, while the composition for experiment 2 are different, 2 mole per liter, 1 mole per liter, and 3 mole per liter for NH3. Then we start from different initial concentrations. At equilibrium, we obtain also different concentrations at equilibrium. Okay. 1. Calculate the equilibrium constant Kc for the synthesis of ammonia at 500 degrees for each experiment. Then, part 2, compare the two values of Kc, then draw a conclusion about the effect of the initial composition on Kc at constant temperature. Okay, the expression of Kc, we have part 3 of the question. The table below shows the composition at equilibrium of the same reaction at T equal 472 degrees. Now we changed the temperature. The composition at equilibrium is 0.0402 mole per liter for N2, 0.172 for H2, and 0.00272 for NH3. Part 3.1, calculate the value of Kc for experiment 3 and compare the value of Kc at 470 degrees with the value of Kc at 500 degrees, then draw a conclusion. Solution. Then Kc 1, Kc for the reaction equal concentration NH3 3 power 2 over concentration N2 times concentration H2 power 3. Kc1 equal concentration NH3 equals 0.157 power 2 over concentration N2 0.921 times concentration of H2 0.763 power 3 equals 0.06. Kc2 for experiment 2, the same. Concentration of NH3 equal 1.82 power 2 over concentration of N2 equal 2.59 times concentration of H2 2.77 power 3 equal also 0.06. To compare Kc1 with Kc2, Kc1 equal Kc2. Conclusion: the two experiments are realized at the same temperature, at the same T. We start from different initial composition. We obtain the same value of Kc. Then the constant of equilibrium, Kc, does not depend on the initial composition of the mixture. If we start from different initial concentrations, since we realize the experiment at the same temperature, we should obtain the same value of Kc. Now, if we change the temperature, we realize the experiment with different temperature. Now Kc3 equal, we'll see if Kc will remain the same or will change when we change the temperature. Concentration of NH3 equals 0.00272 power 2. Concentration of N2 equals 0.0402 times concentration of H2 equals 0.172 power 3. The value of Kc now equal to 0.036. Kc is without unit. The value of Kc at 472 degree different than the value of Kc at 500 degree. 3.2 compare and conclude. Kc at 472 degree different than Kc at 500 degree for the same reaction. Then when we change the temperature, the value of Kc change. Therefore, conclusion, Kc depends only on temperature. It does not depend on the initial composition of the mixture. It depends only on the temperature. Therefore, conclusion, Kc does not depend on the initial composition of the reaction system. It depends only on the temperature. For different initial compositions of the same system, same reaction, we obtain different compositions at equilibrium, but only one value for Kc at the same temperature. This is the end of part 5 and